military technologies will change the world forever, but not in ways you might expect. For example, military robots. Military robots are reshaping the battlefield with advanced technologies that enhance combat, logistics, and reconnaissance. Current systems like Boston Dynamics Spot demonstrate remarkable capabilities, including navigating rough terrain, carrying supplies, and conducting surveillance. These robots use AI and sensors to autonomously analyze their surroundings and make decisions in real time, providing critical support to troops in dangerous or remote environments. Similarly, tracked robots such as the MUTT, also known as Multi-Utility Tactical Transport, can carry heavy loads, serve as mobile power units, and even mount weapons, offering enhanced flexibility on the battlefield. Drones remain at the forefront of robotic military technology. Systems like the MQ-9 Reaper execute long-range surveillance and precision strikes with remote piloting, reducing risks to human operators. Swarming drones, an emerging advancement, operate collaboratively using AI to perform coordinated attacks, surveillance, or electronic warfare. These autonomous swarms can overwhelm enemy defenses and adapt dynamically to changing battlefield conditions, marking a significant evolution in drone warfare. Looking into the future, military robots could achieve full autonomy and integrate advanced AI to perform complex missions without human intervention. Humanoid robots may engage in direct combat, mimicking the agility and decision-making of human soldiers while operating in hazardous environments. Autonomous underwater drones could revolutionize naval warfare, performing stealth reconnaissance or neutralizing enemy ships. AI systems might enable seamless coordination between robots, drones, and human troops, creating highly adaptive battle strategies. The combination of autonomy, advanced AI, and multi-role adaptability will make military robots indispensable tools in the future of warfare. Make sure to stick around until the end, because this video explores autonomous fighter aircraft, cybernetic super soldiers, smart bullets, stealth technology, nanoweapons, and more. Number 2. Hypersonic missiles. Hypersonic missiles are at the cutting edge of military technology, capable of traveling at speeds exceeding Mach 5, 5 times the speed of sound. These weapons combine speed, maneuverability, and precision, making them nearly impossible to intercept with current defense systems. Modern hypersonic missiles, such as Russia's Avangard and China's DFZF, utilize advanced propulsion systems like scramjets, or glide vehicles that travel within the Earth's atmosphere at extremely high speeds. These systems allow hypersonic missiles to alter their trajectories mid-flight, evading traditional radar and missile defense networks. Currently, there are 2 primary types of hypersonic missiles: boost glide systems and scramjet-powered cruise missiles. Boost glide missiles are launched via a rocket into near space before gliding back into the atmosphere at hypersonic speeds. This allows them to strike targets thousands of miles away with minimal warning. Scramjet-powered missiles, on the other hand, use air-breathing engines to maintain continuous propulsion, making them faster and more efficient over long distances. Looking into the future, hypersonic missiles could evolve to include even greater speeds, potentially reaching Mach 10 or higher, while integrating advanced AI for precision targeting and autonomous flight adjustments. These advancements could allow missiles to identify and prioritize targets mid-flight, enhancing their effectiveness in dynamic combat scenarios. Hypersonic systems may also incorporate stealth technologies, reducing their radar signature to near undetectable levels. Additionally, these missiles could serve dual roles, such as deploying swarms of smaller drones or other payloads during flight, further increasing their tactical versatility on the battlefield. Number 3. Autonomous fighter aircraft. Autonomous fighter aircraft are pushing the boundaries of modern warfare, with current advancements showcasing their potential to revolutionize air combat. These unmanned aerial vehicles, also known as UAVs, are designed to operate independently or alongside manned aircraft, leveraging AI to carry out missions such as reconnaissance, air-to-air combat, and precision strikes. Current examples include the XQ-58A Valkyrie, developed by Kratos, which functions as a loyal wingman for piloted jets. Equipped with advanced sensors and AI, It can autonomously follow commands, execute tactical maneuvers, and engage threats, reducing risks to human pilots. These aircraft work by integrating onboard AI with advanced communication systems, enabling them to analyze battlefield conditions in real time. They can identify targets, adjust to changing threats, and collaborate with other units autonomously. This allows them to perform high-risk operations, such as penetrating heavily defended airspaces without endangering human lives. Looking into the future, autonomous fighter aircraft could evolve into fully independent combat systems capable of complex decision-making without human oversight. Advanced AI might enable these aircraft to coordinate in swarms, executing synchronized attacks, or conducting reconnaissance missions over vast areas. They could feature adaptive stealth technology, making them nearly invisible to radar, and hypersonic capabilities, enabling rapid response to threats. Future designs may even allow autonomous aircraft to deploy smaller drones or engage in electronic warfare, disrupting enemy communications and defenses. These developments could fundamentally redefine air superiority and the dynamics of aerial combat. Number 4. Cybernetic supersoldiers. Cybernetic supersoldiers are becoming a reality through advancements in technology that enhance human capabilities on the battlefield. Currently, exoskeletons like Lockheed Martin's Onyx amplify soldiers' strength and endurance, allowing them to carry heavier loads and move faster over challenging terrain. These systems use sensors and powered actuators to mimic natural movement, reducing fatigue and increasing operational efficiency. Similarly, advanced prosthetics, such as those developed by companies like Össur, provide near-human dexterity and strength, offering injured soldiers the ability to return to active duty with enhanced capabilities. Neural interfaces are another groundbreaking advancement. Early-stage technologies like Neuralink are showing potential for soldiers to directly connect their brains to machines. This could allow them to control drones, weapons, or other systems with thought alone, while also enabling real-time access to battlefield data and AI-driven insights. Sensory enhancements, including augmented reality glasses or contact lenses, are also being developed to overlay critical information, such as enemy positions and navigation aids, directly into a soldier's field of view. In the future, cybernetic supersoldiers could feature integrated neural implants that connect them to advanced AI systems, enabling seamless communication and coordination with both humans and autonomous machines. Enhanced bionics might include limbs with superhuman strength, embedded sensors for environmental awareness, and even regenerative capabilities to repair damage. Soldiers could also be equipped with adaptive skin-like armor for protection and temperature regulation. These advancements could make cybernetic supersoldiers the centerpiece of future warfare, blending human resilience with machine precision. Number 5. Smart bullets. Smart bullets are one of the most intriguing advancements in modern weaponry, combining traditional ballistics with precision-guided technology. Current prototypes, like DARPA's X-Acto program, also known as the Extreme Accuracy Tasked Ordnance Program, are revolutionizing how projectiles function. These bullets are equipped with microelectronics, sensors, and small fins that allow them to alter their trajectory mid-flight. By tracking their target in real time, smart bullets can adjust their path to ensure unparalleled accuracy, even when aiming at moving or distant targets. This dramatically improves performance in scenarios where precision is critical, such as neutralizing high-value threats or hitting targets in complex environments like urban warfare. Smart bullets work through a combination of onboard sensors and external guidance systems. The shooter may use a laser designator to mark the target, which the bullet then tracks as it travels. In some cases, the projectile uses heat signatures or advanced imaging to lock onto its target autonomously. These systems make it possible to hit a moving enemy or strike targets behind cover with unprecedented reliability. In the future, smart bullets could evolve into highly versatile tools capable of selecting and prioritizing targets on their own. Future designs may feature even more advanced AI for mid-course corrections, enabling them to adapt to rapidly changing battlefield conditions. Additionally, Miniaturized sensors and propulsion systems could lead to specialized rounds, such as bullets capable of disabling electronic devices or delivering non-lethal payloads. This fusion of precision and adaptability will likely redefine the role of small arms in future conflicts. Number 6. Stealth technology. Stealth technology has advanced significantly, enabling military assets to evade detection and maintain an edge in modern warfare. Current systems, like the U.S. Air Force's B-2 Spirit bomber and F-35 Lightning II, utilize cutting-edge designs and materials to reduce their radar, infrared, and acoustic signatures. These aircraft rely on specialized coatings and angular designs that scatter radar waves, making them nearly invisible to enemy detection systems. The effectiveness of stealth technology comes from its ability to minimize the reflection of radar signals. Low observable coatings absorb radar energy, while carefully engineered surfaces deflect signals away from the radar source. Additionally, these platforms employ heat-dissipating materials and exhaust systems to reduce their infrared signature, making them harder to track with thermal imaging. The latest advancements integrate artificial intelligence to analyze radar patterns in real time, dynamically adjusting stealth measures during missions. Looking into the future, stealth technology could evolve into adaptive systems capable of complete invisibility across multiple detection methods. Future stealth vehicles might use metamaterials that alter their properties on demand, rendering them invisible to radar, infrared, and even visual observation. Hypersonic stealth platforms could further enhance this capability, combining extreme speeds with low observability to evade defenses entirely. Additionally, stealth technology may expand into non-traditional domains, such as naval and space operations, with submarines and spacecraft utilizing similar principles to maintain covert status. These advancements could redefine the role of stealth in future military operations, ensuring dominance across all domains. Number 7. Nanoweapons. Nanoweapons, a cutting-edge field of military innovation, utilize nanoscale materials and systems to achieve unprecedented precision, efficiency, and adaptability on the battlefield. Current advancements focus on the development of nanoparticles for targeted delivery systems, such as explosives or biological agents. These nanoscale materials offer unique properties, including enhanced strength, reactivity, and stealth, making them highly effective in specialized applications. For example, researchers are exploring nanomaterials for more efficient explosives, capable of delivering greater energy while minimizing collateral damage. One of the most promising uses of nanotechnology in warfare is in medical nanoweapons designed to incapacitate rather than kill. Nanobots, for instance, could be programmed to target and disable the nervous system or specific biological functions in enemy combatants. These nanobots could enter the body through inhalation or contact and carry out their tasks with surgical precision, making them ideal for non-lethal takedowns in complex scenarios. In the future, nanoweapons could evolve into autonomous systems capable of operating in swarms. These nanoscale drones might infiltrate enemy defenses, disable machinery, or even deliver targeted chemical or biological agents with unparalleled precision. Advanced nanobots could also adapt to changing environments, repairing themselves or altering their functionality in real time. Future nanoweapons might be capable of targeting specific structures at the molecular level, such as neutralizing enemy equipment by disassembling its components, atom by atom. This evolution could fundamentally transform both offensive and defensive strategies in warfare. Number 8. AI for military decision-making. Artificial intelligence for decision-making is transforming military strategy by providing real-time analysis, predictions, and recommendations. Current advancements leverage machine learning algorithms and neural networks to process massive amounts of data faster and more accurately than human operators. Tools like DARPA's AI Next program and the U.S. military's Project Maven use AI to analyze surveillance footage, identify patterns, and flag potential threats. These systems can sort through complex battlefield data, from troop movements to weather conditions, offering actionable insights to commanders in seconds. AI decision-making tools work by combining data from multiple sources, satellites, drones, sensors, and communications networks into a single operational picture. For instance, AI can predict enemy movements by analyzing historical data, current behaviors, and terrain features. These systems are also being integrated into simulations, enabling commanders to test various scenarios and assess outcomes without deploying resources. The ability to rapidly adapt to dynamic conditions gives military forces a significant strategic advantage. In the future, AI for military decision-making could evolve into highly autonomous systems capable of handling complex, multi-domain operations. Advanced AI could coordinate land, air, sea, and space assets simultaneously, optimizing strategies and reallocating resources in real time. Predictive capabilities may extend beyond immediate threats to include geopolitical trends and long-term outcomes through the use of millions of virtual simulations. Additionally, AI could manage communication networks and cyber defenses autonomously, ensuring uninterrupted operations even in contested environments. These advancements could redefine military decision-making, making it faster, more accurate, and strategically adaptive. Number 9. Laser weapon systems. Laser weapon systems are rapidly advancing as militaries develop directed energy weapons capable of precise, powerful, and cost-effective attacks. Currently, systems like the U.S. Navy's laser weapon system and Lockheed Martin's Helios are demonstrating the ability to neutralize threats such as drones, small boats, and incoming projectiles. These weapons work by focusing high-energy beams of light to heat and destroy targets with pinpoint accuracy. Unlike traditional munitions, lasers offer the advantage of nearly unlimited ammunition as long as sufficient power is available, making them highly efficient for defense. These systems operate through advanced optics and targeting algorithms that track and lock onto fast-moving threats. Once a target is identified, the laser rapidly delivers energy to incapacitate or destroy it, often in seconds. Current systems are primarily mounted on ships or vehicles and are designed to counter small-scale threats, though their range and power are continually improving. In the future, laser weapon systems could evolve into versatile tools capable of engaging larger and more complex targets, such as aircraft or hypersonic missiles. Advances in power generation could enable lasers with greater range and intensity, allowing them to strike at much longer distances. Portable laser systems might also be developed for ground forces, offering soldiers a lightweight, precise weapon for neutralizing enemy drones or vehicles. Additionally, integration with AI could enhance targeting efficiency, enabling simultaneous engagement of multiple threats. These advancements could make laser weapons a cornerstone of future defense strategies, redefining the way wars are fought. Number 10. Space weapons. Space weapons are rapidly becoming a key focus of military innovation as nations prepare for potential conflicts beyond Earth. Current advancements include anti-satellite weapons, which are designed to disable or destroy enemy satellites, and directed energy systems capable of disrupting space-based communication networks. For example, China's anti-satellite missile test in 2007 demonstrated the ability to target satellites in low Earth orbit, highlighting the strategic importance of space dominance. Similarly, systems like the U.S. THAAD, also known as Terminal High Altitude Area Defense, are being adapted to intercept potential threats in near space. Another notable development is the use of small maneuverable satellites known as space drones. These can inspect, repair, or disable other satellites, effectively functioning as space-based weapons. These drones rely on advanced propulsion systems and AI for autonomous navigation, making them versatile tools for both offensive and defensive operations in space. In the future, space weapons could evolve into even more advanced systems, such as orbital platforms equipped with directed energy weapons capable of targeting objects on Earth or in space. Kinetic bombardment systems, often referred to as rods from God, could use tungsten rods dropped from orbit to strike targets with devastating force without requiring explosives. Additionally, Hypersonic delivery vehicles might deploy precision weapons from space at unparalleled speeds. Number 11. Swarm drones. Swarm drones represent a revolutionary shift in military technology, leveraging AI and collective behavior algorithms to operate as coordinated units rather than individual machines. Current advancements have demonstrated their ability to overwhelm defenses, perform surveillance, and execute precise attacks. These drones work by communicating with one another in real time, sharing data to adapt dynamically to changing conditions. For example, DARPA's Offensive Swarm-Enabled Tactics program explores how drone swarms can autonomously navigate complex environments and complete missions, such as reconnaissance or target neutralization. Swarm drones rely on advanced machine learning and sensor fusion to function effectively. Each drone in the swarm acts as a node in a distributed network, enabling the group to maintain operational integrity even if individual drones are lost. This resilience makes swarms particularly effective in contested environments. In a recent demonstration, the Chinese military showcased swarms of drones capable of launching from a single truck and performing coordinated maneuvers, highlighting their potential for battlefield dominance. In the future, swarm drones could evolve into fully autonomous systems with enhanced decision-making capabilities. Future swarms might integrate with larger networks of manned and unmanned systems, coordinating with ground troops, fighter jets, and naval assets. Advances in miniaturization could allow the development of micro-drone swarms for urban warfare or intelligence gathering, while hypersonic swarm drones could disrupt enemy operations at unprecedented speeds. These advancements could redefine air power, making swarms an essential tool in future military strategies. Number 12. Cyber warfare tools. Cyber warfare tools are reshaping the battlefield, with advanced capabilities designed to disrupt, infiltrate, and neutralize enemy digital infrastructure. Current advancements focus on offensive and defensive technologies, including malware, zero-day exploits, and AI-driven intrusion detection systems. Offensive tools like the Stuxnet worm, which was used to target Iranian nuclear facilities, demonstrate how cyber weapons can cripple critical systems by exploiting vulnerabilities in industrial control systems. Such tools operate covertly, infiltrating networks to sabotage operations, steal sensitive information, or manipulate data. On the defensive side, AI-powered cybersecurity tools like IBM's Watson for cybersecurity analyze vast amounts of data to detect and neutralize threats in real time. These systems use machine learning to identify anomalous behaviors, predict potential attacks, and respond autonomously, reducing reliance on human operators. Tools like endpoint detection and response platforms also play a crucial role in securing critical systems from increasingly sophisticated attacks. Looking into the future, cyber warfare tools could evolve into highly autonomous systems capable of executing precision digital strikes with minimal human oversight. AI-driven cyber weapons might analyze an enemy's network architecture in real time, identifying weaknesses and deploying tailored attacks. Quantum computing could further enhance these tools by breaking encryption methods almost instantly, rendering traditional security protocols obsolete. Conversely, quantum encryption could fortify defensive systems, creating unbreakable communication channels. Future cyber tools could also target emerging technologies like autonomous vehicles, smart cities, and even space-based systems, making cyber warfare a central pillar of global conflict strategies. Number 13. Tactical augmented reality. Tactical augmented reality, also known as TAR, is transforming the battlefield by providing soldiers with real-time information overlays directly in their line of sight. Current advancements, such as the U.S. Army's Integrated Visual Augmentation System, integrate AR displays into smart helmets or glasses, offering features like navigation aids, target tracking, and environmental mapping. These systems connect to a network of sensors, drones, and other devices, giving soldiers immediate access to battlefield data without having to look away or use handheld devices. Tactical augmented reality systems operate using advanced sensors, GPS, and AI-driven analytics. For instance, A soldier equipped with this technology can see a live feed of nearby enemy positions, highlighted through AR, while also receiving directions to the next waypoint. These systems can track the movement of friendly forces, reducing the risk of friendly fire and improving coordination in complex scenarios. Some prototypes even allow for communication with unmanned aerial systems, providing aerial reconnaissance directly through the AR interface. Looking into the future, tactical augmented reality could evolve into highly advanced, lightweight systems integrated into contact lenses or retinal implants, eliminating the need for bulky headsets. These systems could feature enhanced AI capabilities for real-time threat assessment and decision-making. Future systems might also incorporate biometric monitoring, displaying health data and alerts for soldiers in high-stress situations. Additionally, they could allow seamless integration with robotic units and autonomous drones, enabling soldiers to command and interact with these assets directly through AR. These advancements will redefine situational awareness and tactical precision on the battlefield. Number 14. Railguns. Railguns are one of the most exciting advancements in modern weaponry, leveraging electromagnetic forces to launch projectiles at hypersonic speeds without the need for explosive propellants. Current prototypes, like those developed by the US Navy, are capable of firing projectiles at speeds exceeding Mach 7, reaching ranges of over 100 miles. Railguns work by using a powerful electric current to generate magnetic fields, accelerating a projectile along conductive rails. This process creates an enormous amount of kinetic energy, enabling the projectile to destroy targets through sheer velocity and impact force. One of the key advantages of railguns is their cost-effectiveness compared to traditional missile systems. Each shot uses relatively inexpensive projectiles and eliminates the need for explosive warheads, reducing logistical and operational costs. Railguns are also highly versatile, capable of targeting incoming missiles, aircraft, or ships with incredible precision and minimal warning. Looking into the future, railgun technology could evolve to become more compact, efficient, and powerful. Advances in energy storage, such as next-generation capacitors and solid-state batteries, could enable railguns to fire continuously without overheating or requiring lengthy recharge times. Future railguns might also integrate with AI systems for real-time targeting and guidance, further improving accuracy. Additionally, space-based railguns could emerge, using electromagnetic propulsion to launch satellites or deploy kinetic energy weapons for orbital defense. These developments could position railguns as a cornerstone of both terrestrial and space-based military strategies. Number 15. Quantum radar. Quantum radar is an emerging technology that could revolutionize detection systems by leveraging quantum mechanics to achieve unparalleled accuracy and stealth detection. Current advancements involve the use of quantum entanglement to detect objects that traditional radar systems struggle to identify, such as stealth aircraft or hypersonic missiles. Unlike conventional radar, which relies on radio waves, quantum radar systems use entangled photons to create a highly sensitive detection field. The key to quantum radar's potential lies in its ability to detect even the smallest disturbances in quantum states. When an entangled photon interacts with an object, its paired photon is observed at the radar base. This interaction is detected and analyzed, allowing the radar system to accurately determine the object's location, speed, and size. This mechanism allows quantum radar to see through traditional countermeasures, such as radar-absorbing materials or electronic jamming. In the future, quantum radar could evolve into highly compact, energy-efficient systems capable of integrating with satellites, aircraft, and ground-based installations. These systems might operate across vast distances, providing real-time tracking of multiple targets in complex environments like urban or dense jungle terrains. Advanced AI could further enhance quantum radar by analyzing quantum data and identifying threats instantly, even in cluttered or contested spaces. With its unparalleled accuracy and resistance to countermeasures, quantum radar could become a cornerstone of global security and early warning systems. reshaping how militaries approach detection and defense. Number 16. Electromagnetic pulse weapons. Electromagnetic pulse weapons, also known as EMP weapons, are becoming a critical focus in modern military strategy due to their ability to disable electronic systems without causing physical harm. Current advancements include both nuclear and non-nuclear EMP devices. Nuclear EMP weapons generate powerful electromagnetic waves as a byproduct of a nuclear detonation at high altitudes, capable of crippling electrical grids, communication networks, and military systems over vast areas. Non-nuclear versions like high-powered microwave weapons use directed electromagnetic energy to target specific systems, offering precision without collateral damage. EMP weapons work by disrupting the electromagnetic fields essential for modern electronics. They induce currents and voltages that overwhelm circuits, effectively disabling unshielded devices. Modern systems like Boeing's CHAMP, also known as Counter-Electronics High-Powered Advanced Missile Project, demonstrate how high-powered microwave technology can selectively disable enemy infrastructure. These systems rely on directed energy to ensure that only targeted devices are affected, making them ideal for disabling command centers, air defense systems, or critical infrastructure. In the future, EMP weapons could become more compact, portable, and precise. Advanced delivery systems, such as drones or hypersonic missiles, could allow for rapid deployment against high-value targets. Future EMP technology might also integrate with cyber warfare tools, combining physical disruption with digital infiltration. Enhanced shielding technologies in military systems may lead to an arms race in EMP resilience versus EMP potency. These developments could make EMP weapons central to modern conflicts, reshaping the dynamics of electronic and cyber warfare. Number 17. Ultra-frequency sound weapons. Ultra-frequency sound weapons, often referred to as sonic weapons, represent a fascinating and non-conventional advancement in military technology. These weapons use high-frequency sound waves to incapacitate or disorient targets without causing permanent physical harm. Current systems like the long-range acoustic device are already in use for crowd control and area denial. This device emits focused sound beams at frequencies and intensities capable of causing extreme discomfort, disorientation, and even nausea, effectively neutralizing threats without lethal force. These weapons work by manipulating sound frequencies to target the human body's natural resonance points, disrupting balance and cognitive function. High-frequency sound waves can also penetrate barriers, making them effective for use in urban environments or against fortified positions. Sonic weapons can be calibrated to create various effects, from dispersing crowds to incapacitating enemy combatants. In the future, ultra-frequency sound weapons could evolve into highly versatile systems with precise targeting capabilities. Advanced AI could be integrated to identify specific individuals or groups, minimizing collateral effects. Portable sonic weapons might become standard for military and law enforcement use, offering non-lethal solutions in a wider range of scenarios. Additionally, future designs could include weapons capable of using sound to disrupt electronics or machinery, potentially disabling drones or vehicles. As materials science advances, sonic weapons might become smaller, more efficient, and capable of greater customization, ensuring their place as a critical tool in future conflict scenarios. Number 18. Adaptive camouflage technology. Adaptive camouflage technology is revolutionizing stealth capabilities, allowing soldiers, vehicles, and even buildings to blend seamlessly into their surroundings. Current advancements include materials that can dynamically change color, texture, or temperature to mimic the environment. One breakthrough example is the use of metamaterials in electrochromic panels, such as those developed by the U.S. Army and research teams at institutions like MIT. These systems rely on tiny, programmable structures that manipulate light, enabling surfaces to shift colors or patterns in real time. This technology works by utilizing advanced sensors to analyze the environment and generate a corresponding camouflage effect. For instance, wearable adaptive camouflage suits can project the surrounding terrain onto their surface, rendering the wearer nearly invisible. In addition to visual stealth, some systems incorporate thermal adaptation to mask heat signatures, making them undetectable to infrared sensors or thermal imaging devices. In the future, adaptive camouflage could evolve into fully integrated systems that extend beyond visual concealment. Future designs may include smart fabrics that not only adapt to the visual and thermal environment, but also dampen sound or electromagnetic signals. Vehicles equipped with 360-degree adaptive panels could become virtually invisible to radar and optical systems, while wearable technologies might become lighter, self-healing, and powered by ambient energy. Advanced AI could further enhance these systems by predicting environmental changes and adapting in real time, making adaptive camouflage a cornerstone of next-generation stealth technologies. Number 19. Next-generation body armor. Next-generation body armor is advancing rapidly, offering soldiers enhanced protection, mobility, and functionality on the battlefield. Current innovations include lightweight materials like graphene and advanced ceramics that provide superior ballistic resistance while reducing the overall weight of armor systems. For instance, modern body armor, such as the Talos prototype, also known as Tactical Assault Light Operator Suit prototype, integrates advanced materials with a powered exoskeleton, aiming to protect soldiers without hindering their agility. One key advancement is liquid armor technology, which uses shear thickening fluids. These materials remain flexible under normal conditions, but harden instantly upon impact, distributing energy to prevent penetration. This allows for lighter and more adaptable armor that molds to the wearer's movements while maintaining a high level of protection. Additionally, adaptive camouflage features are being integrated into some systems, providing both protection and stealth capabilities. In the future, body armor could evolve into fully integrated systems with AI-driven enhancements. Smart armor might include embedded sensors that monitor the soldier's vital signs, detect injuries, and even administer medical treatments like blood clotting agents or pain relief. Advanced materials could enable self-healing capabilities, where damage to the armor repairs itself automatically. Future designs may also incorporate exoskeleton-like components that amplify strength and endurance, allowing soldiers to carry heavier loads without fatigue. These advancements could redefine personal protection, making next-generation body armor a cornerstone of future military operations. Number 20. Underwater drones for naval warfare. Underwater drones, or unmanned underwater vehicles, also known as UUVs, are revolutionizing naval warfare with their ability to operate autonomously in the ocean's depths. Current advancements include systems like the U.S. Navy's Orca XL UUV, also known as Extra Large Unmanned Undersea Vehicle, which can conduct long-range missions such as surveillance, mine countermeasures, and payload delivery. These drones operate autonomously or via remote control, relying on advanced navigation systems, sonar, and AI to perform their tasks even in challenging underwater environments. These vehicles work by using onboard sensors and AI-driven algorithms to map terrain, detect threats, and execute missions without human intervention. For example, smaller drones like the Remus 100 are designed for shallow water operations, identifying mines or conducting reconnaissance near enemy coastlines. Meanwhile, larger drones such as the Sea Hunter can travel thousands of miles autonomously, tracking submarines and other targets with minimal oversight. In the future, underwater drones could evolve into highly versatile platforms capable of stealth operations and multi-role functionality. Future designs may include swarms of small, cooperative, unmanned underwater vehicles that can coordinate complex maneuvers to overwhelm enemy defenses or conduct large-scale surveillance. Advanced propulsion systems could allow these drones to operate faster and quieter, making them harder to detect. Integration with other naval assets such as surface ships and aerial drones could create seamless networks for real-time data sharing and coordinated attacks. These developments are likely to make these vehicles a central element of naval strategy in the decades to come. Thanks for watching. Make sure to watch this next video about emerging technologies